So let me start with a few announcements first. So first of all, the assignment 4 is due on Friday. And there will be no extensions. That way I can post the solutions online this weekend, and you'll have them available for studying. Then a reminder to make sure you see one of the admin assistants to fill in the course surveys. Or the course evaluations. Next Monday, that's I guess the 8th of December, we'll do a review session. It'll last as long as needed. So if you're in a classroom and you have a class coming after you, maybe you should take this particular session not in a classroom, but somewhere that allows you to stay longer. And the goal is that we'll go through some of example problems that I'll prepare that will be typical of what's on the exam, and then I'm available to answer any questions that you have on previous assignments. So I highly suggest that you start studying before that so that you come prepared with questions. And I'll just answer your questions until there are no more questions. And then finally, the exam. Is on the 12th of December, which is a Friday, next Friday. And it will be 2 hours long from 12 p.m. to 2 p.m. Central Time. So for those in Rapid City, that's 11 a.m. to 1 p.m. So based on the emails, I didn't get any objections to that date. So this is your last chance to object. If not, I'll proceed with booking a room, and I'll follow up on an email of where the exam will be located. Any questions about that? Okay. So let's start with a summary. So last week, we looked at the Hamilton-Jacobi equation. So if we step back a little bit, with this Hamiltonian method of doing things, we introduced canonical equations. And we saw that we could pretty much use any function that we want, the so-called generating function, and from that, rewrite the Hamiltonian in the equations of motion using coordinates that are somewhat arbitrary. And so you have a lot of freedom in how you redefine the description of a problem. And the Hamilton-Jacobi equation came about when we chose a particular transformation where the transformed Hamiltonian was identically zero. That means none of the coordinates appear in the transformed Hamiltonian, so that they're all cyclic and constant. And that condition if you remember, for a canonical equation, or canonical transformation, sorry, or canonical transformation with a generating function S, the transformed Hamiltonian, well, this is updating very slowly. I'm actually in Canada, so I apologize if it takes a long time for the notes to update. So for a canonical transformation with generating function S, the transformed Hamiltonian K was given by the untransformed Hamiltonian H plus di S by di T. Now, if we choose K to be equal to 0, then we get Hamilton-Jacobi equation. And the Hamilton-Jacobi equation then is just H plus di S by di T equals 0. And it's a partial differential equation for S. Okay. And so we then have that the transformed momenta, the capital PI, we set them to equal to alpha I, which were constants, and then the capital QI we set equal to beta I, again constants, since none of the canonical variables appear in the transformed Hamiltonian, and those were also given by di S by di alpha I. I'll give that a minute to update. Okay, any questions about that? We then did an example where we applied the Hamilton-Jacobi equation to the simple harmonic oscillator. And we indeed saw that the transformed Hamiltonian was 0, and that the alpha i's and beta i's are constant, and then we could transform back using the properties of canonical transformations to the solutions for the little pi and the little qi. Okay. So today, again, a highly theoretical subject called action angle variables. That's section 8.5 in the notes. So we're going to use this formalism of the action angle variables. It's sort of an extension to the Hamilton-Jacobi method, and we use it when the Hamiltonian does not depend explicitly on time. And we saw that when the Hamiltonian doesn't explicitly depend on time, that function S that comes about in the Hamilton-Jacobi equation, that's called Hamilton's principal function. When the Hamiltonian doesn't depend on time, that function can be separated out into a time-independent part and a time-dependent part. So we can write that the function s, which depends on the lowercase qi, the alpha I, and t, can be written, so that's called Hamilton's principal function. Let me just write that in. It can be written in terms of a time-independent term, which we call w, which would depend on the lowercase qi and the alpha I, minus the energy of the system times t. And that w is called Hamilton's characteristic function. And then E is the energy of the system. Okay. So if you recall from the properties of the canonical transformations, the lowercase pi, the momenta, are given by di w by di lowercase qi. And then the Hamiltonian, h, which depends on the lowercase qi and the lowercase pi, but the lowercase pi we can write as di w by di qi, is equal to the total energy. Okay? So this is particularly the situation that we're going to consider when we talk about these action angle variables. Okay. So we're going to go a little bit further in our assumptions, and we're going to consider the case where the function w itself can be written, or the w function itself is called separable. So just now we made the assumption that s is separable. That means we can separate the dependence on the variables from the dependence on time. And we can also make the assumption that w is separable. That means that we can separate the different coordinates into different functions. So if I assume that the w, which depends, on the q1 to qn, alpha 1 to alpha n, that it can be written as w1 of q1 and alpha 1 plus wn of qn alpha n. So what we're essentially saying is that the system is separable in the different coordinates. So that means the motion in the different coordinates is independent of each other. So you can think of, for example, a mass that's connected to two springs that are perpendicular to each other. The oscillation that's from one spring can be completely independent from the oscillation that's in the other spring. So we can think of that motion as separable in the two coordinates. Or another simplification could be, for example, you consider the Earth, Moon rotating around the Sun, all in a plane. You can almost consider the motion of the Moon around the Earth to be separate from the motion of the Earth around the Sun. Obviously, that's not exactly true, because otherwise the Moon wouldn't circle the Sun along with the Earth. But to some approximation to first order, the motion of the Earth around the Sun is separate from the motion of the Moon around the Earth. So that's an example of a system where you'd have maybe two generalized coordinates. One is the angular position of the Earth and the Sun, and the other is the angular position of the Moon with respect to the Earth. Those are almost independent from each other, and they can be treated almost separately. Okay? So So that's physically what this mathematics corresponds to. Okay. So for this action angle variable, we're going to consider, in addition to all that, cases where motion is periodic. So the whole point of this action angle variable approach is that we can learn about a system without actually solving for the system. For example, a simple harmonic oscillator, we'll be able to determine the frequency of that harmonic oscillator without having to actually solve for the equations of motion. And this action angle variable is a formalism for finding the frequencies of a system without having to solve for the system. Okay? So of course you have to consider systems where the motion is periodic. And so there's two such cases of periodic motion that one can define. So one is called vibration. So we consider periodic motion such as, in the first case, vibration. So if I draw a diagram in phase space of the kind of motion that we call vibration, so if I can do a one-dimensional case where I draw Q and P, then vibration is a motion where in phase space you have a closed loop. So a simple harmonic oscillator is an example of a vibration type of periodic motion. Both the coordinates and the momentum return to their initial value. Same thing with a pendulum, where it's a small oscillations of a pendulum. The angle, the position of the pendulum, keeps returning to its same value as when the momentum has the same value as well. Okay. The other case that's different is what's called rotation. It's another case of periodic motion. If we draw a rotation in phase space, then the motion will look more like a sine wave. So the motion is periodic in the momentum. The momentum keeps returning, oscillating back and forth between fixed values, but the position coordinate keeps increasing. So think, for example, of a pendulum, but now the pendulum has enough energy that it can go around the top. So it's basically rotating. So if you describe the angular position of the pendulum, if it's at the bottom, it's at 0, theta equals 0, and it goes around once, then it's at theta equals 2 pi. If it goes around again, it's at theta equals 4 pi. So something that's rotating, the angular position, in this case, Q, keeps increasing, but the momentum oscillates between two different things. Okay, so those are the two cases, vibration and rotation, the two cases of periodic motion. So that is the kind of motion that we're going to consider. Okay? So we start by introducing what's called the action variable, which we're going to call capital JI. And we define these capital JI to be the integral. I'm going to write the integral as, I forgot the calculus term for this. Circular integral? The integral sign, we have a circle on it. The term escapes me. Anyway, so we're going to define the capital JI as the circular integral of the lowercase pi and then integrate it over the dqi. And the integral is over one period of the motion. So these capital JIs we call the action variables, and we just introduce them as this integral. And then we'll see in a bit that these JI are effectively similar to the momenta in some transformed Hamiltonian, so they're like the capital PI after some canonical transformation, and that we're able to write the new Hamiltonian in terms of these JI. So for each coordinate that's separable, there is one of these action variables, JIs. So if I use the property of the canonical transformation, which we wrote earlier, that the lowercase pi was equal to the di wi by di qi, this JI integral is the integral of di wi, and wi depends on qi and potentially all of the alphas, di qi dqi. Okay, that's just inserting the definition or the properties of the canonical transformation that relates pi to the wi's. Okay? So we don't know what these w functions are, but in principle, if you knew what they were, we could do this integral, and then we could get, from doing these integrals, we can get the JI as a function of all of the alphas. Right? It was the Q will drop out because you're doing a di W by di Q, and then you're integrating over Q. So the result, JI, doesn't depend on Q anymore. It only depends on the alphas. So the assumption is that you can find these W's, and then you can do these integrals, and you can find the action variables J in terms of the constants alpha, which you also don't know. And now finally, we make the assumption that we can invert these equations, and that we can express the alpha I and express the alpha I themselves as functions of the J's. Okay, so make the assumption that we can find what the J's are in terms of the alphas, and we can invert those transformations. So this means that we have a way of going back and forth between the J's and the alphas. All right? And so we can rewrite the characteristic functions, which was W of the Qi and the alpha I, we can rewrite as the function W of the Qi's and the Ji's, because we can replace, we know what the transformation are between alphas and J's. So similarly, we can write the Hamiltonian, which originally depended on the Qi's and di W by di Qi. Remember, di W by di Qi is simply Pi. Or sorry, that's di W by di alpha I, which is equal to Pi. Di alpha I. So we can write that Hamiltonian in terms of the Qi and di W's by di capital Ji's. And as well, Hamilton's principal function, S of Qi and di W by di alpha I, we can rewrite as the W of the Qi Ji minus E times T. Which is also equal to the W of the Qi and Ji minus H times T, since the energy is equal to the Hamiltonian. Okay. So far, it's been very confusing, but all we've done is we've introduced these new variables, capital Ji, which we call the action variables, and they're defined as that integral of the Pi dQi, and then presumably one can rewrite all the Hamilton-Jacobi equation and all the equations of motion by using the J's. So you put the J's instead of the alphas into the Hamiltonian. So effectively, we've chosen a new canonical transformation where the Ji's replace or are the momenta, the new transform momenta, which we called capital Pi in the past. Okay. So if we use the properties of canonical transformations, then the lowercase pi are given by di s by di lowercase qi, and then the capital Qi given by di s by ji. All right, this is for a canonical transformation of the second type. So I wrote the CT for canonical transformation. And so the function S still satisfies the Hamilton-Jacobi equation. And new canonical momenta, these capital Ji, are still constants of motion. So we still have, from the Hamilton-Jacobi equation, right, that the capital Pi, which are the capital Ji, are equal to constants. And similarly, the capital Qi, which in the past we've called beta I, are constant as well. So we're just again doing the Hamilton-Jacobi equation, but we've introduced, instead of the capital Pi, the Ji, with a very specific definition. But of course, we must still conclude that they are still constants of motion, because that was the whole point of the Hamilton-Jacobi equation. Okay. So we've introduced one new kind of variable, the action variables. So there's a mistake in the notes here. So we've introduced the JI, these action variables. So we're now going to introduce ones that we call WI, and we'll call those the angle variables. So let us introduce lowercase wi's as the angle variables. And the lowercase wi's are going to be defined as di uppercase W, which depends on Q1 to Qn, as well as J1 to Jn. It's the di W by di Ji. So in the case, of course, where the W is separable, this is probably going to be equal to just di W1 by di J1. Okay. So now, consider the constants. Beta I. So the constants beta I, which are the capital QI, right? They're given by di S by di capital Ji. If I plug in our formula for S, that's di by di Ji, but since S is separable, that's di by di Ji of W of the QI and Ji minus H times T. I'll just let this update. I don't know why it's so slow to update. Okay, so remember the beta i's are constants. It's just above there. And they're given by di S by di Ji. And S, we said, were separable in terms of a W, and the part depends on the coordinates, W, and the part depends on time. And then the W's, we showed that we can express in terms of the J's instead of the alphas. Okay. Now we just introduced these angle variables W because of this. Because now note this equation where I have beta I equals di by di Ji of W minus di by di Ji of H times T. So the di capital W by di Ji is the lowercase w that we just introduced. So these beta i's, which remember are constants, are equal to the lowercase wi minus di H by di capital Ji times T. So remember, beta I is a constant. Everything else is not a constant in that equation. So if I introduce, if I rewrite this equation, I can say that Wi is equal to beta I plus nu I times t, where I've introduced nu I to be di H by di capital Ji. So I'm just rearranging this equation. So I'm keeping the Wi and I'm moving the di H by di Ji to the other side, and then I'm calling the di H by di Ji nu I, the Greek letter nu, which we normally use for frequency. Okay? So whatever these W's are, they're given by a constant, beta I, plus this nu I, which we don't know what it is, times t. And I called it nu I because this equation kind of looks like maybe it's a frequency based on the dimensions. So I give it the letter we usually use for frequency. Okay? So the final part now is to figure out if nu I really does correspond to some sort of frequency. So remember, we're considering periodic motion, right? So we can ask ourselves, so let's have the system have a period. So let capital Ti be the period of the motion of the coordinate Qi. All right, so remember we had a system that we said was periodic and separable. So for example, one of the Qis could be the position of the moon around the Earth, and that can have its own period. And a separate Qi with a different period could be the position of the Earth around the Sun. All right, so it's a case of you have two coordinates, and they're separable motions, and they each have their own period associated with it. So now let's consider the change in the angle variable W. So consider the change in the lowercase w over a period capital Ti. So delta Wi, lowercase w's, I'm going to define to be Wi evaluated at the time Ti minus Wi evaluated at time t equals 0. And so there's two ways that we can evaluate this delta W. One is to look at the equation that we just found, where we wrote Wi was equal to beta I plus nu I times t. All right, so the beta i's are constant. So if I use that equation to evaluate Wi or delta Wi, then I find that delta Wi equals nu I times capital Ti, right? That's if I use beta I minus plus nu I at Ti minus beta I plus nu I at 0. So one way to write delta Wi is to say it's equal to nu I times capital Ti. That's the change in this sort of arbitrary looking variable Wi that we introduced. So now the other way to calculate delta Wi is to explicitly evaluate the change in Wi using all the definitions that we've introduced for the different variables. So the other way to calculate delta Wi is to say, let's take the integral over one period and integrate dWi, the differential Wi. Let me just let that update. Okay, so that's the other way to calculate delta Wi. So let's go ahead and evaluate that. So we have the integral, and the dWi I'm going to write as a sum over the j coordinates of dWi by dQj dQj. So I'm going to change this into an integral over the Qj. So that's equal to the integral over one period of the sum over j. And now the dWi by dQj, remember the definition of Wi was di capital W by di capital Ji. So I'm going to keep the di by dQj, but the lowercase Wi I'm going to write as di capital W by capital Ji. That was the definition of Wi. Okay. Now I'm free from the properties of derivatives and integrals to bring the di by di Ji outside of the integral. So I have di by di Ji integral of the sum over j of di W by dQj dQj. Now, the properties of canonical transformation, di W by, so di capital W by dQj is Pj, lowercase pj. So I can write this as di by di Ji outside of the integral sign. And then I have the sum over j. Now the di W by dQj I write as Pj, and I still have the dQj. Okay. Now I can, of course, swap the order of summation and integration. So I have di by di Ji, and I'm going to put the sum over j, then I'm going to write the integral, and then I have Pj dQj. Okay? It seems to be slow to update. So now I have di by di Ji, sum over j, integral over one period of Pj dQj. But now the integral Pj dQj is exactly the definition of capital J. I guess it's confusing to use j as the summing index as well. Sorry about that. So let me write this as di by di capital Ji, sum over lowercase j, and then that integral is now capital J indexed lowercase j. Now that's of course a trivial thing to evaluate. So I have di by di Ji of the sum over j of the j's underscore j. So there's only one term in that sum when I take the partial derivative that's not going to be equal to 0, and that's the term where lowercase j is equal to I. Right? And so that's going to be dij I by dij I. And so that's going to be equal to 1. Okay? So it appears that this delta Wi, which we saw to be already equal to nu I times t, is also equal identically to 1 based on the definitions that we used. So if I equate those two, so I have delta Wi, on the one hand, it's equal to nu I times ti, and on the other hand, it's equal to 1. That means that nu I is 1 over ti. So remember, t is the period, whatever it may be, of that particular coordinate I. And we've just shown that this nu I, which if you recall a few lines back was equal to dih by dji, that nu I is indeed the frequency associated with that motion. So we just proved that this nu I, given by the derivative of the Hamiltonian with respect to ji, really is the period of the motion. Okay? So that's it for the introduction. This seems a little bit far-fetched. So let's do a practical example where hopefully you'll see the deeper significance of this. So we've effectively found a method to determine the frequencies of a system without actually having to solve the equations of motion for that system. So we'll do an example, which is example 8.6 in the notes, where we can see how maybe we can apply this. So this is, we're going to determine the frequencies for two-dimensional simple harmonic oscillators. So I'll draw an ugly sketch of such a device. You could think of it a mass M, and it's connected to two different springs. And it can oscillate in, say, two different perpendicular directions. And so there's two springs, and each have a different spring constant, K1 and K2. And the motion of the mass is in two dimensions, which we'll label as Q1 and Q2. Okay? And so this is such a periodic separable system, right? If this is in the plane, so I'm sorry, there's no gravity here. Okay? So intuitively, you feel like the oscillations along the Q2 axis are going to be independent of the oscillations around the Q1 axis, right? So this is an example of such a separable system. So the way to use these action angle variables, the first step is to write the Hamiltonian for the system, right? So the Hamiltonian for the system, which in this case, I hope you have enough practice that you can write it down by inspection. So that'll be 1 over 2m times p1 squared plus p2 squared, the generalized momentum in the two direction, plus a half k1 q1 squared plus a half k2 q2 squared. Okay? So you have a case of kinetic plus potential energy in this case. So the Hamiltonian doesn't depend explicitly on time either. So it's a constant and it's equal to the total energy. So our first step is to now write this out using the Hamilton-Jacobi equation. So we want to write, so we use the fact that lowercase pi is given by di w by di lowercase qi. And so we can write this, the Hamiltonian, as h given by 1 over 2m. So p1 squared I'm going to write as di w by di q1 squared, plus 1 over 2m. p2 squared I'll write as di w by di q2 squared, plus a half k1 q1 squared, plus a half k2 q2 squared. And so that's got to equal to the total energy E. So this is a case where the Hamiltonian doesn't depend on time. So Hamilton's principal function, S, can be written in two parts, a W and a part that's E times T. So the coordinate part and the time part can be separated out. And then if you put that W back in, with the definitions for a canonical transformation, you can write the Hamiltonian in terms of di W's by di Qi's. So we've gotten rid of the Pi's. Okay? Now, this is a case of separable motion. So we can write, so it's separable. That means we can write the W, which depends on Q1 and Q2. We can write it as a separate function, W1 of Q1 plus W2 of Q2. Okay? Now, since the W has been written out as separate functions of Q1 and Q2, the partial differentials are the same as total differentials. Or they're indistinguishable, right? So I can rewrite the Hamiltonian as 1 over 2m dW1 by dQ1 squared plus 1 over 2m dW2 by dQ2 squared plus a half K1 Q1 squared plus a half K2 Q2 squared equals E. So that's a differential equation, which is kind of two differential equations, one for W1 and one for W2. Now, if you look at this differential equation, there are terms that depend only on Q1 plus terms that depend only on Q2 equal to a constant. All right? So that means that the terms that depend on Q1 are a constant plus the terms that depend on Q2 are a constant. So we can write this as, we can introduce two new constants. So the parts that depend on Q1 are a constant, and the parts that depend on Q2 are a constant. So I can write that 1 over 2m dW1 by dQ1 all squared plus a half K1 Q1 squared equals a constant, and I'm just going to call that alpha 1. And then similarly, I'm going to write it for the other degree of freedom, 1 over 2m dW2 by dQ2 all squared plus a half K2 Q2 squared equals alpha 2. All right, that's just recognizing the fact that I have the sum of two things that don't depend on the same variables equals a constant. So those two things must individually be constants. Now, at this point, if I were to follow the Hamilton-Jacobi method, I could actually solve quite easily, right, these two ordinary differential equations for the W1 and W2, and I'd be done. I can solve for the motion of the system. Right, these are very straightforward differential equations to solve for W1 and W2. So the problem could be solved, and I can get the equations of motion by finding what the functions W1 and W2 are. But the point of the action angle variables is that we don't need to actually solve these equations to figure out some stuff about the system, and in this case, the frequencies of the system. I'm not going to solve these differential equations. Instead, I'm going to note that the momentum, so these two equations look exactly the same, right? So I'm not going to keep writing them out with 1s and 2s. I'm just going to put i's in them, and I could be equal to either 1 or equal to 2, right? So remember that the lowercase pi is given by dwi by dqi. So it's given by di w by di qi, but the w is separable, and because it's separable, the partial and total differentials are going to be the same. Okay? So I can calculate now, by rearranging that equation, the two equations that I have above, I can solve for what dwi by dqi should be, right? So that's simply equal to the square root of 2m times alpha I minus a half ki qi squared. Right? From one of these equations, I can get dw1 So I can use the equations above to isolate what dw1 by dq1 is, and that's also equal to pi. So I've just written what pi is equal to. So remember, the goal is to get the ji, the capital Ji, which are given by the integral of lowercase pi dqi. So that's why I wanted to write pi in terms of qi, so I can take that integral with a circle on it to get the capital Ji, so that we can write eventually the Hamiltonian as a function of the Ji. So I need to do this integral. I need to integrate this function pi that I just wrote here, that's square root of 2m alpha I, over qi. Okay? Now it turns out it's not mathematically super convenient. So I'm going to re-express the qi. I'm just going to introduce a new variable, theta I. So I'm going to introduce theta I such that qi is equal to the square root of 2 alpha I over ki, that's all square rooted, sine theta I. You can just think of this as the definition of theta I. So I'm just reparameterizing qi in terms of theta I. Think about it when you do an integral. You have an integrand and you do a change of variables. You have maybe an integral of 1 over square root of 1 minus x squared. You realize that if you make a change of variables where the x is an angle, then maybe it's sine theta, so 1 minus sine squared theta is cos theta, and then the integral becomes easy. So that's all we're doing, right? Because we want to do that integral. And so I already know what I can tell that it's going to be more simple if I introduce this change of variables. So it's simply a change of variables to do the integral. So when you introduce a new variable to do an integral, you need to figure out what dqi is in terms of the new variable. So dqi is given by the square root of 2 alpha I over ki. So if I take the derivative of sine theta I get cos theta I d theta I, right? That's simply from doing dqi by d theta I. And so it turns out that writing qi in terms of this theta I can write the pi into something much more simple and much more pretty to integrate. So if I plug that in, remember we have that pi is that square root. So I can rewrite pi is equal to square root of 2m times alpha I minus, so it's a half k1 qi squared. And if I plug in the new definition for q1, that's my alpha I times minus a half ki 2 alpha I over ki sine squared theta I, so it's all qi squared. So the ki's simplify, the 2 alpha i's factor, and I'm left with a 1 minus sine squared theta I. So that gives me that the pi is equal to square root of 2 m alpha I cos squared theta I. Okay. So now I found pi in terms of something that's a little bit more easy to integrate. So now I can finally calculate my ji's, capital Ji's. The capital Ji is the integral over 1 period of lowercase pi dqi. So that's the integral of the pi which we just wrote. That's 2 alpha I cos squared theta I. And then the dqi in terms of d theta I we just wrote up there above. So that's square root of 2 alpha I over ki cos theta I d theta I. Okay. So that's equal to, if I express out evaluate the square root and simplify, and take stuff that's constant outside of the integral, I have 2 alpha I square root of m over ki, the integral over 1 period of cos squared theta I d theta I, which is equal to 2 alpha I square root of m over ki. Now the integral over 1 period is from 0 to 2 pi, since I'm now using an angle, cos squared theta d theta. Oops. and that integral of cosquared is just pi. And so I find finally that my ji is equal to 2 pi alpha I square root of m. Okay. Now remember, earlier we said the whole point was to do the ji's to evaluate that integral, and then hopefully you get an expression of the j's in terms of the alphas that you can invert and express the alphas in terms of the j's. Because the Hamiltonian we know how to express in terms of the alphas. Okay? So indeed, we found a rather simple relation in this case between the ji and the alpha I. Okay, so this is very trivial to invert. So we can invert this, and we get that alpha I is ji over 2 pi square root of ki over m. Okay? Okay, so now we have the alpha i's in terms of the ji's. So remember, the Hamiltonian we wrote as alpha 1 plus alpha 2. We separated out the terms that depended on Q1s, and we said that was all equal to alpha 1, and the terms that depended on Q2, we said that was all equal to alpha 2. So we wrote the Hamiltonian is alpha 1 plus alpha 2. Now we have alpha I in terms of the ji. So I can finally get to what I wanted, which was the Hamiltonian in terms of the action variables j. So the Hamiltonian is 1 over 2 pi. That's common for both alpha I. Then I have alpha 1 plus alpha 2. So I have square root of k1 over m times j1 plus square root of k2 over m j2. And that was the goal, was to find the Hamiltonian in terms of these j's. Now remember, the frequencies that are associated with the degrees of freedom are given by di h by di ji. All right? So now we have two j's, so we have two frequencies. So we have nu 1 is given by di h by di j1. And so that's a trivial integral to evaluate, derivative to evaluate, right? So di h by di j1 is 1 over 2 pi times the square root of k1 over m. And nu 2 is di h by di j2, and that's 1 over 2 pi square root of k2 over m. So remember, these are frequencies, not angular frequencies, so that's why there's a 2 pi in them. There's, of course, the result that you expect, right? The frequency of a harmonic oscillator is square root of k over m for the angular frequency. And the frequency is the angular frequency over 2 pi. So we, derived a rather trivial result that you probably could have picked off from the Hamiltonian before you started, but that's only because you know what the answer is. And the reason you know that the frequency of a simple harmonic oscillator is square root of k over m is because you've solved the ordinary differential equation of motion for the simple harmonic oscillator and integrated over one period to find that the frequency is square root of k over m. What we did here is quite different. We wrote out the Hamiltonian for the system. We did this crazy action angle manipulation, and we found the frequencies directly without having to solve the equations of motion. And that's truly the power of this method. And so that means that you can think of other much more complicated systems where the equations of motions aren't easy to integrate, but you can still pick out the frequencies by using this method. Okay? So that's all I had about this. Are there any questions? Sorry that it didn't refresh very quickly, but I hope you're at least able to somewhat follow along in the printed notes as I derive the equations. Okay, so this is not the kind of thing that I expect you to pull out of thin air and give you a completely different problem and understand how to solve it. I think you should be able to understand the method, and if the math works out to be simple, then I expect you should be able to do it. But in this case, you have to make a guess about the change of variable, for example, from Qi to theta I, and that's not trivial. Okay, so this is your last chance to complain about the exam being on Friday, December 12th. I haven't received any objections by email, and actually had suggestions to have it then, so I'll send you an email about the actual class, or the location of the exam. So on Wednesday, we'll have a much lighter lecture. This will be the connection between everything that we've done and quantum mechanics. Then I suspect we'll either have some time for some questions or finish early on Wednesday. Next Monday we'll have, again, like I said, a review session where I'll do some examples, and I highly recommend that you study before then so that you come prepared with specific questions. Okay, so if there's no more questions, then that'll be it for today. Thanks, everyone.